Probability. Today, probability is an important branch of mathematics with applications in statistics, economics, industry, science or technology, etc. Terms in probability: random experiment, an experiment in which all the possible results are known in advance but none of them can be predicted with certainty, is called a random experiment. For example, tossing of a coin, throwing of a die. Outcome: the result of a random experiment is called an outcome. In tossing a coin, we have two possible outcomes: head, represented by H, or tail, represented by T. In throwing a die, we have 6 possible outcomes: 1 or 2 or 3 or 4 or 5 or 6. Equally likely outcomes. A given number of outcomes are said to be equally likely if none of them is expected to occur in preference to the others. For example, if we toss an unbiased coin, the outcomes head or tail are equally likely to occur. Sample space. The set of all possible outcomes of a random experiment is called sample space. It is denoted by S or omega. The number of elements in set S is denoted by Ns. Let us have a look at the table given below. It shows the sample space and the sample points or numbers of elements in the sample for a few random experiments. A well-shuffled pack of 52 playing cards contain 26 red cards and 26 black cards. Out of these 26 red cards, 13 are heart cards and the remaining 13 are diamond cards. Out of the 26 black cards, 13 are spade cards and the remaining 13 are club cards. Each set of these 13 cards has 3 picture cards of king, queen and jack, and 10 number cards bearing numbers from 2 to 10 and an ace card. Event. A subset of the sample space is called an event. That is, a set of all favorable outcomes is an event. Events are generally denoted by capital letters A, B, C, D and so on, except S. For example, if 2 coins are tossed, let A be the event of getting at least 1 tail. Here, the favorable outcomes are as follows. Event A is the set of elements TT, TH and HT. The number of elements in the event A is denoted by NA. Here, NA equals to 3. Types of events. Certain event. An event which contains all the sample points is called a certain event. Sample space S is a subset of itself. Thus, the sample space is a certain event. Example: throwing a die and getting a score from 1 to 6 is a certain event. Impossible event. An event which does not contain any sample point is called impossible event. An impossible event is a null set. It is denoted by phi. Example: a coin is tossed. Getting 2 heads or 2 tails is an impossible event. Elementary event. An event consisting of only one sample point of a sample space is called an elementary event. Example: a die is thrown. Let A be the event of getting a score on the upper surface, which is divisible by 5. Here, sample space S equals to the set of numbers 1, 2, 3, 4, 5 and 6. Event A equals to the set having only one number, that is 5. Therefore, NA, that is, number of elements for event A, equals to 1. Therefore, event A is an elementary event. Let B be the event of getting score divisible by 3. Then, event B equals to the set of two numbers, that is 3 and 6. Therefore, NB, that is, number of elements for event B, equals to 2. Therefore, event B is not an elementary event. Complement of an event. Let A be an event in a sample space S. The set of all outcomes which are in S but not in A is called complement of an event A and is denoted by A dash or AC, that is, represented by the shaded part in the figure. Example: a die is thrown. A is the event of getting an odd number. Then, sample space S is the set of numbers 1, 2, 3, 4, 5, 6 and A is the set of numbers 1, 3 and 5. Then A dash is the set of numbers 2, 4 and 6. Therefore, A dash is the complement of event A. The complement of a certain event is an impossible event and vice versa. Therefore, S dash equals to phi and phi dash equals to S. Note: A union A dash equals to S. A intersection A dash equals to phi. The complementary set of A dash equals to A. Let A and B be two events in a sample space S. A and B are subsets of S. Hence, A union B and A intersection B are also subsets of S. Therefore, A union B and A intersection B are also events in S. A union B represents the occurrence of either A or B or both A and B. Therefore, A intersection B represents the occurrence of both A and B. Mutually exclusive events or disjoint events. Let S be the sample space and A and B the two events of S. A and B are called mutually exclusive events or disjoint events if they do not have any sample point in common. That is, A intersection B equals to phi. For any event A intersection A dash is always equal to phi. Therefore, A and A dash are mutually exclusive events. Therefore, two complementary events are always mutually exclusive events, but the converse is not true. Example: when a coin is tossed, let P be the event of getting head. That is, P is the set of H and Q be the event of getting tail. That is, Q is the set of T. Here, events P and Q are mutually exclusive as well as complementary. Two complementary events are always mutually exclusive events, but converse is not true. Phi and S are mutually exclusive events and complementary also. Exhaustive events. Two or more events are said to be exhaustive events if their union is a sample space. Example: throwing of a die is a random experiment. Sample space S equals to the set of numbers 1, 2, 3, 4, 5 and 6. Let A be the event of getting a number less than 4. So, A is the set of numbers 1, 2 and 3. Let B be the event of getting a number greater than 2. So, B is the set of numbers 3, 4, 5 and 6. Therefore, A union B equals to the set of numbers 1, 2, 3, 4, 5 and 6, which is equal to sample space. Here, A union B equals to S. Therefore, events A and B are exhaustive events. A union A dash is always equal to S. Therefore, A and A dash are also exhaustive events. Probability of an event. The probability of an event A of a finite sample space S is written as BA and is measured as probability of event A equals to the number of sample points in event A upon number of sample points in sample space, that is S. Probability of event A equals to NA upon NS. Properties of probability. Probability of null set represented by phi is equal to 0, and probability of sample space, that is S, equals to 1. That is, the probability of an impossible event is 0 and the probability of a certain event is 1. Proof. Probability of an impossible event equals to n phi upon ns equals to 0 upon ns, that equals to 0. So, probability of event S equals to number of elements in sample space S upon number of elements in sample space S, that is ns upon ns, which equals to 1. If S is the finite sample space and A is an event of S, then probability of event A is greater than or equal to 0 and smaller than or equal to 1. Proof. As A is equal to or the subset of S, phi is equal to or the subset of A, which is in turn equal to or the subset of S. N phi equals to 0. NA is smaller than or equal to NS. Therefore, NA is greater than or equal to N phi and smaller than or equal to NS. Therefore, NA is greater than or equal to 0 and smaller than or equal to NS. Dividing the inequality by NS, we get, therefore, probability of event A is greater than or equal to 0 and smaller than or equal to 1, as NA upon NS equals to BA. Thus, the probability of any event lies between 0 and 1, both inclusive. If S is the finite sample space and A is an event of S, then BA dash equals to 1 minus PA, where A dash is the complement of event A. Proof. A union A dash equals to S and A intersection A dash equals to phi. Then, number of elements in set A union A dash equals to number of elements in sample space S, and number of elements in set A intersection A dash equals to 0. Therefore, NA plus NA dash minus NA intersection A dash is equal to NS. As number of elements in set of A intersection A dash equals to 0, NA plus NA dash equals to NS, or NA dash equals to NS minus NA. Dividing both the sides by NS, we get NA dash upon NS equals to NS upon NS minus NA upon NS. As NA dash upon NS equals to PA dash and NA upon NS equals to PA. Therefore, PA dash equals to 1 minus PA. Example: 3 coins are tossed simultaneously. Find the probability of following events. 1. Getting exactly 2 heads. 2. Getting at least 2 heads. 3. Getting no head. 4. Getting at the most 2 tails. S is the sample space. S is the set comprising of following elements. Therefore, number of elements in sample space S equals to 8. 1. Let A be the event of getting exactly 2 heads. Looking for the elements in sample space having exactly 2 heads, we get therefore NA equals to 3, as PA equals to NA upon NS. Putting the values of NA and NS, we get 3 upon 8. Therefore, probability of event A equals to 3 upon 8. 2. Let B event of getting at least 2 heads, that is, 2 or more heads. Looking for the elements in sample space having at least 2 heads, we get therefore NB equals to 4, as PB equals to NB upon NS. Putting the values of NB and NS, we get 4 upon 8 equals to 1 upon 2. That is, probability of event B equals to 1 upon 2. 3. Let C be the event of getting no head. Looking for the elements in sample space getting no head, we get therefore NC equals to 1, as PC equals to NC. Putting the values of NC and NS, we get 1 upon 8. Therefore, probability of event C equals to 1 upon 8. 4. Let D be the event of getting at the most 2 tails, that is, 2 or less than 2. Looking for the elements in sample space, getting at the most 2 tails, we get. Therefore, ND equals to 7, as PD equals to ND upon NS. Putting the values of ND and NS, we get 7 upon 8. Or probability of event D equals to 7 upon 8. Alternative method. Because D is the complementary event of C, that is, D equals to C dash, and as PD equals to PC dash equals to 1 minus PC. Putting the value of PC, we get 1 minus 1 upon 8 equals to 7 upon 8. Therefore, probability of event D equals to 7 upon 8. Example: Sachin buys a fish from a shop for his aquarium. The shopkeeper takes out one fish at random from a tank containing 4 male fish and 6 female fish. What is the probability that the fish taken out is a female fish? Solution: total fish in the tank equals to 4 plus 6 equals to 10 fish. Therefore, number of elements in sample space equals to 10. Let A be the event that the fish taken out of the tank is female. Then, number of elements in event A is equal to 6. As probability of event A is equal to number of elements in event A upon number of elements in sample space. Therefore, probability of event A is equal to 3 upon 5. This means that there are 60% chances that the fish taken out is a female. The possible outcome or result is known, but we cannot predict the result.